In engineering and physics, finding the exact balance point of a flat object is crucial. When density is uniform, the centroid is purely geometric. However, when density varies across the surface, we must use calculus to find the center of mass. If a plate is heavier on one side than the other, the balance point shifts toward the denser region. We describe this distribution using a density function, rho of x and y, which tells us the mass per unit area at any point. Our goal is to calculate the coordinates x bar and y bar. To do this, we must first determine the total mass and the moments about the axis by integrating across the entire region are occupied by the lamina. The total mass, m, is the double integral of the density function over the region R. We can think of this as summing up all the tiny mass elements, dm, which are equal to the density at a point multiplied by the area. Next, we find the moments. The moment about the y-axis, mi, measures the tendency to rotate around that axis and uses distance x. Conversely, the moment about the x-axis, mx, uses the distance y. Note the subscripts are swapped. The coordinates of the center of mass are simply the moments divided by the total mass. This gives us the weighted average position of the mass in both the horizontal and vertical directions. Let's find the center of mass for a triangular lamina where the density increases as we move right. The region is bounded by the axis and the line y equals 1 minus x, with a density function of 1 plus x. First, we calculate the mass. We integrate the density function 1 plus x with respect to y from 0 to 1 minus x, then with respect to x from 0 to 1. Evaluating this gives us a total mass of 2/3. Now we find the moment about the y-axis by adding an extra factor of x to our integral. After integrating x plus x squared over the region, we find the moment mi is equal to 1/4. Similarly, for the moment about the x-axis, we include a factor of y. Integrating y times the density function over the same triangular bounds yields a moment mx of 5/24. Finally, we divide the moments by the mass. Our x-coordinate is 3/8 and our y-coordinate is 5/16. Notice the center of mass is shifted slightly toward the denser right side of the triangle. If the density were constant, the centroid would be at 1/3, 1/3. Because our density increased with x, the center of mass moved right and slightly down relative to the geometric center. Remember, geometric symmetry only helps if the density function is also symmetric. If the density varies across a line of symmetry, the center of mass will move away from that line. When setting up your double integrals, choose the order of integration that makes the boundaries easiest to describe. Sometimes integrating with respect to x first simplifies the algebra significantly. To summarize, always calculate the mass first, then the moments. Keep your variables straight, use x for the y moment and y for the x moment, and always divide by the total mass at the end. Think about a square where density is equal to y. This means the top is heavier than the bottom. Would you expect the y-coordinate of the center of mass to be higher or lower than the geometric center at 0.5? Since the density increases as y increases, the mass is concentrated at the top. The calculation confirms that y bar is 2/3, which is indeed greater than 0.5. Thank you for learning with us. Generated by Vision Solve AI.